All right, so now that we know how to plot the displacements, let's do something harder. Let's try to plot the strains. What we really want to get at is something like this here. We want to see how, or we want to end up with what Abacus has here, which is the well, let's take the LE11, the strain of this object. I'm not quite sure that this is the exact same material properties as we have, but it's something close to. So let's see what we need to do. And yeah, so what we need to do here is we need to loop over all the elements, and we need to loop over all the integration points, and we need to compute the strains from that. Let's see here, I have prepared a Wikipedia page. There we go. So this is how to compute or what the strain is actually made up of. Now we only focus on this part here, which is the 2x2 strain matrix, and we see here that we need to compute the derivatives of this, and then see here that these guys are actually the same if the material is isometric. Okay, we could also do it this way, but yeah, I think this is more graspable what's happening if we define it component-wise. All right, let's compute it. Let's see what we can do here. So first things first, we need to define number of elements. So we do number of elements, and actually let's just grab all of it. So number of elements and the number of local nodes, and we get that by using size here. Then we grab number of nodes, and well, the dimension, and that's by grabbing the size of p. Okay, we will also need the integration points, and we have that function already. So that's Gauss, so we can use that. So the Gauss points and the Gauss weights, Gauss weights here, are given by the function Gauss, which we should have in our working folder. And yeah, we need the Gauss order here. So let's see, where is the Gauss order defined? Gauss order, there we go, Gauss order. So just put that in there. Okay, so far so good. Now let's see if we run this evaluate selection here. You can see that we have actually I'm not in, yeah, GP, let's write it out here, 2 points, right? So let's just try to loop it, and we'll see. For IEL 1 to Nele, number of elements, and inside here we want to loop again twice actually. So for yeah, I is equal to 1 to number of Gauss points. How many Gauss points do we have? Well, we have number of Gauss points, length GP, like this, and yes, and this loop, and then inside of this for J is equal to 1 to number of Gauss points, right? So we're looping twice over the elements, one for each element dimension, or Gauss dimension. We have 2 times 2, right? So we have a bilinear element, and then we have four corner nodes. Let me just quickly show it here maybe. So if we zoom into this, we have 1, 2, 3, 4. So that's what we're looping over. Once over these, 1, 2, and then once over these, 1, 2 here. So that's 4 in total. So yeah, so this is gonna loop 4 times. Okay. All right. So we need the Gauss point in there. So let's you can use Xi and Eta. I like to use R and S, just because it's, well, less to write. So R is equal to what? The Gauss points in I and S is equal to Gauss point J. Should be outside Gauss point J. Okay. Now what happens if we just run this? Let's see here, R and S. Just gonna run this up to, well, here one time. Yeah, I think I need to press run, and there it ran. Something, yes, get rid of that. Okay, so it ran once, and then yeah, sorry about this. Let's run it again. Quit debugging and run again. Yeah, so 4 times, as we can see here, and these are the points. So lower left corner, and then yeah, these are the corners, right? Okay, so once we have done this, we need to evaluate the basis function in here now. Okay, so remember the basis function is given by this thing here, and if you just well, let's open this. You can see here that we can use this stuff, and actually I made this into a function, so I can actually call it with base function now. So I can actually choose any function I want here. So that's why I did that. So you can just replace it. So this is a sort of alias now to this function here. So it's the same. It's just the calling flag has changed. Okay, so you see here I used xi and eta, so I just replace xi with r and eta with s, and then xc and yc. These are the coordinates for my elements, and I don't have them yet, so I need to create them here. So let's do that. So first I need to define the I nodes for this element, which are nodes. Get rid of that. Nodes IEL, like this. So for IEL, and this is great when you're in debugging mode, you can hover over these things and see what's happening. So you can just evaluate this now. Evaluate selection, and you can hover over it and you see what it is. So for the current element, which is 1, the nodes for this element are 1, 4, 5, and 2. Now I can create xc from P, right? So I access these nodes, I nodes, and well, the first one actually. So the first dimension, that's x, and let's just copy this in here, right, like that. So now I have these. I can't press F9. I'm gonna stop recording if I do. All right. So now I have x, c, and y, c. So if I evaluate this now, let's see if I'm actually inside of this. Yeah, I am. This is the last point. So I have R, I have S, so I can evaluate this now. So just evaluate this. So I get phi here, phi. This is the what's it called? Yeah, the basis function, and then the derivatives of the basis function here, d phi dx, d phi dy, and then the determinant of the Jacobian. All right. So what now? Well, now I need to compute these guys here, the partial derivatives of u with respect to x and y. Okay, I don't have the partial derivatives of u, I have the partial derivatives of phi with respect to x. So how can I get that? Well, the thing is, and this is the beauty of the Galerki method, and if you multiply the phi dx with x, you will get dx, right? The coordinates. And if I grab ux here by going into u1 I nodes, right? Because it's the same now, and well, it's just a vector, it's not a matrix, so I can just grab that one, and then I grab the y component, which is here. It's 2. Oops, that's supposed to be 2. Come on, there we go, and evaluate that. We have e nodes. Sorry about that. There we go, and there we go. So So the solution for this element in the nodes are well, what you see here in the x and y component. Now, if I were to compute or multiply ux here with do a dot product with dphi dx and ux, I would get du dx. Okay, so if I multiply, if I do a scalar multiplication with dphi dx with ux, I will get du dx. So let's do that. So this is then uxx, right? So it's the derivative, or let's do it like this. It's du dx, or actually it's dux dx. Okay, so I can do it with a dot product, right? So I can take this, I can take my derivative and ux. So basically what this does is it takes the first component of dphi dx and it multiplies it with the first component of ux, and then it adds the next component, which is 0, well, the next component, which is 0.0616 with negative 0.0025, and it adds that. So it adds it together. So this is what this does. So if I evaluate this now, I get a scalar value, which I should get. Okay, but the thing is that dot is not necessary here. I mean, if I multiply the vector, this vector, if I just do matrix multiplication with this vector, with these two vectors now, I will get the same output. That's because this is a row vector and this is a column vector, and they're the same size. So let me get rid of the dot here and just do standard multiplication like this, and let's verify that I'm not full of bullshit. Evaluate selection and the same output. All right, great. So it's a bit cumbersome to write ux dx. You can just write uxx. That means that it's the x derivative of ux. Okay, great. Now that we have established that, let's copy this and do uyy. Okay, so that's du y dy. Okay, so we need the derivative and we need uy. All right, so once that is done, we need two more. We need, let's see here, we need dux dy. This is the second component, so this is y, and we need duy dx. So let's grab that. So the xy, right? So this is the first one here. This is dux dy. So we need to change this one. And then the fourth one is dyx, duy dx. So duy, this is supposed to be y, and this is supposed to be x. So now we have all of them, and now we can create epsilon here by grabbing these and putting them in here. So let me just move this here. All right, a nice cheat sheet. Okay, so let's just do eps is equal to a matrix, and this is uxx, and then we have open parenthesis uxy plus uyx, right? Yes, divided by 2, and let's just do this. It's easier to read. Now the second component here, epsilon, what is it, 2,1, is actually the same as this one, right? These components here, you can just change them around, it's the same. So we just copy this and throw it in here, comma uyy, and that's done. All right, so if we evaluate all of these guys here, evaluate, and then we evaluate eps, there we go. This is the complete tensor for this Gauss point. Okay, now when we are inside of Abacus, you can take, well, you can take E11 here, you can take E122, you can take E33, they just have it for some reason, it's not really here, and you can take E11, I'm not having E11, right? No, yes, I'm in something completely different here, never mind that. So I can actually have E11 as well if I'm in the right component, which I'm not apparently. So let me just close this down, and now what we want to do is we have to export this. We save it in a data structure. Since we are in a Gauss point right now, there are several different ways of doing this. We can do it element-wise, so we have to integrate it for the complete element, and then we save it into an element array. Or a little bit more complicated is to save it into a nodal array, and then take this nodal array and weight it with the mass matrix. But this nodal mass matrix does not exist, so you have to create it. Let's do both ways. All right, so what we're going to do here is do the element one first. So we need to create it, and let's do it outside of the loop here. So let's call it let's do the principal. Let's do the principal one first. So EE, and let's do something like this. EL, just to, well, just to make sure that this is something completely different from what we are going to use later. Okay, so this is called pre-allocation. So we build the whole thing, and we just throw in a bunch of zeros in there. So this is a number of elements big, and it's a scalar vector field. Oh, it's a scalar field. So we have just one value inside there, and then it's an yellow long. And if we evaluate this, it's 50 times 1. Okay, so now we can throw in a bunch of stuff in there. So the thing that we're going to do here is just grab E11, that's yellow, right? And yeah, actually no, we have to do it like this. We have to create a new variable, eps yellow. Let's do it like this. Yellow is equal to what? Well, eps yellow again, and it should start as it should be 1 1, and it should start out as 0. Okay, and we have to integrate now. So we throw in a bunch of stuff in here. What do we throw in? We throw in this value, the first value, which is 1 1. Okay, but this is not an integration. We have to multiply this with the weights, the Gauss weights. Do we have Gauss weights? Yes, there we have them. So Gauss weights, I times Gauss weights again, because we have 2 dimensions, j, and then the determinant of the Jacobian, which is the area of this now deformed, which is the area of the element. Okay, so this will do it. This will create the this thing here, which should be a scalar. So if we just run this now again, so quit debugging, save, and run, we should have a value here, and this value now is at the very end of this this loop here. Okay, so now we can grab that outside of the loop, of course, because it's now assembled. It's integrated fully, and we grab it and put it in here. So take this one, and we take the ith element, and we throw this thing in there. Done. Okay, so once we do this for all elements, we can visualize this. So let's do that now. This should be pretty fun. I have done it previously here, but I'm not gonna cheat this time. Let's close this. It actually opens when I do stuff in the debugger. I'm gonna go ahead and do this. Moves further down. All right, so new cell, right visualize. Actually, you can exit out of the debugger. And let's do start at X figure. And let's just go ahead and do HP is equal to patch. Okay, so what are we gonna patch? Let's see. It's not cheating if I've done it before, right? I mean, I've done it with you guys before, so let's go ahead and do viz, maybe here. Yep, there we go. So I'm gonna grab this and throw it in here. Right, you can do the same. So faces are nodes, vertices are P plus U1 plus U2 times the scale, which we set here. Scale is equal to 10. Okay, now the C data is UR here, and the face color is interp. That we need to change. So let's just do C data. C data is now this. Okay, and replace C data with this here, so that we can reuse this code later. And then we can do interp. What happens if we do that? Just run this thing. We run and it says, warning, error creating or updating patch, error in value of property face vertex C data. You will see what it's lying about, because it's not, there's no property that I'm setting that's called face vertex C data. I'm setting the C data. Well, there's no such thing as C data. I mean, when you set C data, it depends on what you have in the face color. If you have flat, I mean, if you have interp, then for interpolation's sake, there needs to be a color data for each vertex. Okay, and there is none, because C data here, this vector, if we place a thing here, this is 50 times 1, and nodes is also 50 times 4. It is not 78 times 2, or 78 times 1 would be fine as well. Then it would use the interpolation data, and UR is that. So if we do size UR, you can see it's 78. So that would be fine here. But this is not. So we can't use interpolation. So we need to use flat here. Okay. So remove this and run it again, and we get this thing. All right. So we need to set the axis. So do axis equal, and run it again, and we get that, which looks kind of nice. It's just a little bit too few elements. So go up here and set the element size to maybe 2, rerun it, and there we go. This is the first principle E11 element-wise, right? So for each element we have a value. Okay, let's get rid of this actually. Axis equal off, and let's do. We have actually done it before. Color map jet and color bar, like this. All right, so this should look more like something in here. So if we zoom out, turn off this, turn on that, and let's go to quilt and do, yeah. So this is looking quite similar to what we have here, sort of, right? You can see the similarities. Yeah, and even the values are sort of the same, but this is a completely different model, I guess. Yeah, so it's sort of the same. Great. So now you see what needs to be done in order to create this this thing. You have to loop over all the Gauss points and do a computation. That's why when you are inside of Abacus, when you're selecting what output you need, be sure to only select the stuff that you really need in the field outputs, which is located here, field output request. Because the larger your model is, the more, well, looping will be done, and the more stuff will be needed to be exported. Okay, so more calculations equals more time. So we want to minimize that.